Sometimes when I'm trying to solve a difficult problem, which I don't know very well, I'm going to browse the internet and look for solutions there that other people have found. And sometimes it then happens that I find a description or an algorithm, but the chances are pretty high that that algorithm is not written in Haskell, but that it is written in an imperative programming language or in some pseudocode. So I thought it would be nice in this episode to look at this kind of problem, to how to go from an imperative description of an algorithm to Haskell code. So, and as an example, we're going to use an algorithm which I am reasonably familiar with. So in that sense, it's not a representative example, but it's simple enough to hopefully fit into an episode, even though it may last slightly longer than usual, namely Dijkstra's shortest path algorithm on graphs.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Right, so it is just an example, right? So, and I'm not planning to spend a lot of time explaining or motivating the algorithm at all, because that's not the point. We're going to look at how to translate pseudocode into Haskell code. Nevertheless, to have a little bit of setting the stage, right? So the setting is that we have a directed graph where we have costs at the edges, and we're trying to find the shortest path from a source node to a particular target node. So like, for example, from A to F here. And there are multiple ways to get from A to F. We can go here A, B, D, F. Then we get 4 plus 7 plus 1 is 12. Or we can go A, C, E, F. Then we have 5 plus 4 is 9 plus 3 is also 12. Or we can go A, C, E, D, F. And that is 5 plus 4 is 9, 10, 11, which is actually the shortest path ideally here, right? So that is the one that we would want to find. That is sort of the scenario we're in. If we look at Wikipedia, we find a lengthy description, and at some point we get to some sort of textual explanation of how the algorithm is supposed to work. And then if we scroll even further down, we do get a pseudocode version of the algorithm. And this is the version that I want to look at. It's not actually a particularly nice version. There is even sort of a slightly better one further below, but like both of them suffer from some problems. But like normally, you wouldn't necessarily know that, right? And you have to start somewhere. So you have a description of something and you want to translate it into Haskell. So let's just try to do that, right? Without trying to understand very much about what this is actually doing. Let's just try to see if we can get somewhere. So let's switch to our Haskell code. I have copy-pasted essentially the Wikipedia pseudocode here to the right, so that we have it here. And I have a started Haskell module, and in Haskell, we typically start with the types, right? So when one of the first things we have to talk about is how do we represent our graphs? And graphs are a thing in programming where, whether you are in functional programming or in imperative programming, that doesn't really make a lot of difference. There are, I would almost say, millions of different ways to represent graphs, and in particular scenarios, different representations are useful. So here I've chosen one which is reasonably functional, but also should be easy to compute from whatever other representation you might have. So we just have the list of vertices. We can present the neighbors, the direct successors of any vertex. And for any two vertices, we can produce a cost. And the idea is that, in terms of totality, we are never going to call the cost functions on two vertices which are not connected by an edge. But in principle, it is also easy to make a total, right, and or to let it crash, but whatever you prefer. And so we keep the vertex type and the cost type parameterized. although we are going to make some constraints to it. And one aspect which is important for Dijkstra is that the costs are non-negative. Otherwise, the algorithm is not going to work as expected, at least. And so that is our starting point. And let's continue with the types. Let's continue. Let's look a little bit at how this algorithm is structured and what kind of data structures are occurring in it, right? So we have this function here, which takes a graph, something like this, and a source, which is the starting vertex that we are interested in as an input. And actually, this version is not taking the target vertex. It is actually trying to compute the costs for all target vertices. It is a relatively short modification or post-processing step to make it from one source to one target.
So just to be clear, what we want to know here is, given a particular source vertex, for every vertex in the graph, what is the shortest path to that other vertex, right?
Right, exactly. And so the way or the data structures that are being used here are, first of all, there are two arrays here which are indexed over the vertices in the graph. And this dist array is essentially holding some form of cost, acquired knowledge about the distance, right? And the pref array here is going to actually store the path. That's the idea, that is pointing from vertices to other vertices, and is going to always back point to the previous vertex, so that in the very end, we hope that the dist array is going to hold all the shortest distances to all the vertices, and that pref is for every vertex going to point back along the shortest path towards the source node that we started with. So these two things we have to somehow model in Haskell. So we have to find a type for prev, and we could use an array, but typically, in my experience, very often, if you use an array in a function in an imperative language, then the best data structure to by default switch to is actually a finite map. The reason being primarily that, we are not concerned about efficiency all too much, but arrays in imperative languages have very good lookup and update behavior. Functional arrays have a very good lookup behavior, but very bad update behavior, extremely bad. Linear update. If you update a single element in a functional array, you have to copy the whole array. And finite maps have logarithmic insert and lookup and update and everything. So they typically are better behaved. So I'm going to go for essentially representing this pref and this dist array using something. Essentially, dist is going to be map from the vertex type to a cost. I'm going to say something about this in a moment, and pref is going to be a map from the vertex type to the vertex type. Okay. So there is this infinity and undefined mentioned here. Perhaps we can briefly talk about this. So finite maps have the additional property that arrays have to somehow be initialized, but finite maps start out empty. So there is this concept that something is not in the map. And here we are actually initializing to somehow exceptional values, right? The algorithm is setting all the initial dist entries to something called infinity, and all the all the initial pref values to undefined. So perhaps we can just get away with this, right? So let's just try to assume for the time being that not in map for dist means infinity, right? Whatever exactly the meaning of that is, that will hopefully become clear. And not in map for pref means undefined, right? Or let me also capitalize this to make it clear that I mean this in the sense of the pseudocode. And then we have one more data structure which is used throughout, and that is this capital Q here. And that is essentially a container of vertices. And if you want to make the algorithm efficient in the end, then you actually need to be a little bit clever. You should be using something like a heap or a priority queue for this. But like as a starting point, and also to keep it simple, I'm going to use lowercase q because we are in Haskell, and I'm going to just use a list of vertices in order to represent this. Okay, so that's the general idea. And now, if you look at the structure of this function, there is essentially something which I would call an initialization phase here, right? And then there is a loop. And whenever you have a loop in an imperative program, you want to turn it into a recursive function. That is sort of a general concept, right? In Haskell, this loop should become a recursive function. And what are the parameters of this recursive function? Well, they're all the things that are changing throughout the loop. So if we look at the loop, what is being changed here? Well, Q is updated. For example, it says remove U from Q here. So this list is changing. And dist and prev are also potentially updated in this loop, in this while loop. So all these three things are potentially changing. So they all need to become parameters to this loop. Do they also need to become outputs of it? That's the other question. No, not necessarily, because a loop is essentially going to look like we have loop of some parameters, and then we do some stuff, possibly like with a let that define some things. And then in the very end, we're just going to call the loop again, except if perhaps we have a condition where we break, like if something holds, then we return immediately. But otherwise, we are just going to effectively call the loop again in the end with like changed parameters. So just by like changing the parameters in the recursive call, we can simulate these updates to these variables. The only thing that we need to return from the loop is what we need to like use afterwards. So we don't need the queue anymore after the loop, but we do need to return dist and prev if we want to be faithful to this pseudocode. So so we're going to pass q and dist and prev to the loop, but only going to return dist and prev from it. And because dist and prev are sort of connected to each other, I actually want to define a type that is sort of holding just these two things. I'm going to call it info, like Dijkstra info, or you can call it state or intermediate result or something like that. But basically the idea is that this just holds like a map VC, and this holds a map VV. And again, like not in map means infinity, and not in map means undefined. Right? And yeah, we can derive show for this. And I'm making these strict. I don't want to go too much into this, but like basically, this is the stuff that is changing all the time. There is nothing in this algorithm that benefits from laziness. One can think about this a little bit, but basically everything has to always be evaluated. So we're just going to make sure that this info is always fully evaluated. I think that is a good default in this particular case. And we are also going to use strict finite maps, which are like strict in both the spine and the values. Okay, so that's that. Now let's actually look at a few more things. So there is this, like I've already been talking about this list data structure or queue data structure, and we have this operation here, which looks a little bit like, I mean, it pains me a little bit to see something like this. So what are we actually trying to do here at the beginning of the loop? So we are trying to check whether this list or container is empty. And if it is not empty, we're going to try to scan across this container and find the element in it, like the vertex in it, for which the distance is minimal. Actually, this is phrased in a very weird way. I mean, like Etzko pointed this out to me before. I did not even see it, because like the U is sort of like the result of this statement, but it is also being used as an input. So let me actually just rewrite this. So what I think the algorithm means here, we want to traverse all the vertices U prime that are in Q. And for each of these, we want to compute the distance, or the currently known distance. And then we want to select the one that has the minimal distance and call that U, right? So I'm actually going to try to like to isolate this, because also particularly because it is with our list approach is going to be a very inefficient operation, to isolate this into a separate function. And I'm going to call this minViewOn. And the idea is that minViewOn is taking a function that, let me still phrase this sort of roughly with the types that we want to use it at, that for a vertex can extract the cost, like the distance, and then we're going to operate on a list of vertices, and we're going to maybe return a minimum value. That is the vertex that has the minimum cost, and the remaining list.
Yeah, so this is not just doing line 12 of the pseudocode, but also line 13, right?
And also 11, actually. I mean, to some extent,
yes,
right?
Yes.
So we're going to combine essentially these three things into one, where we are going to say, okay, like given this cost function and given this list, it's either the list is empty, then we return nothing, or the list is non-empty, then we can find a minimum and return the stuff that removes that. So let's try to do this. So we have this F, and if the list is empty, then we return nothing. And if we have F and we have a non-empty list, yeah, so here, like I was arguing with myself a little bit. I mean, one could also be sort of more precise and actually create a non-empty list. I'm going to just unsafely, which I usually hate a little bit, call the minimum by function from the list library on this now known to be non-empty list XS, and that should then be safe, right? So I'm going to say let m equals minimum by. Minimum by is from the list library. I need to pass a function to minimum by, which is related to this f. And I want to look at this in this XS. And then I am going to, in the end, just return m, and I'm going to delete the m from XS. And yeah, so I need to require various different things. EQV for now, that's fine. Probably I need more in the end, because, I mean, what does minimum by need? Minimum by needs a thing that goes from V to V2 ordering. And yeah, so this is something like we want to, like compare would be the normal thing to put there, right? That would be the standard ordering from the ord class. But what we want to do is we want to get two nodes, two vertices, and we want to essentially apply this cost function to each of these, and then compare that, f of v1 and f of v2.
Maybe it would be clear if you write it without compare, like just with an inequality. Oh no, you can't. Oh yeah,
you can't. I need compare.
Yeah,
because,
sorry.
And then I need to require ord c. But I think this is fine, right? I mean, like we have to say how to compare two things, and we already kind of know how, like we are requiring to know how we compare these result values of the function, but we're applying this function to the two values in order to get the actual costs, and then we're comparing those.
Right. We don't want to compare the vertices, we want to compare the costs.
Yeah.
And one thing to point out here is that just to point out that this is implementing the API that we want. in a real implementation, you probably want to do something slightly different here, right? This is not.
Yeah. I mean, this is sort of like a place where we isolate various bits of ugliness, right? I mean, so like both this sort of like slightly unsafe call to minimum by, but also there is a double traversal here because we are like first determining the minimum and then removing it again. Like if we had a better data structure, like many of the better data structures are actually offering something like this as a built-in operation. Right. So it kind of makes sense from that perspective to extract it here. We could simplify slightly here if you prefer this. I mean, this is actually available as comparing f in the libraries if you want. I mean, comparing is a predefined function in data.org, which does just this thing. Right? Okay, so let's look a little bit further even. Let's look at this infinity. And so we're looking at the minimum distance here, right? But the distances can be infinity. They're not just numbers. That is the idea. So we have some sort of slightly extended notion of number with an extra value. And I decided to not put sort of like infinity as a possible value into the map, but to say that if something is not contained in the map, I want to consider it infinity. But that means that if I actually want to use something like the minimum of these values, where some of them may be in the map and others may not be in the map, I need to be careful because a lookup from a map is returning a maybe. And if I like compare something, like compare nothing with just 3, right? In Haskell, nothing is considered to be smaller than just. Anything that is constructed using just is always going to be greater than nothing. But what we want is that, and I think this is the reason why they call this infinity, right? That if we compare something which is not in the map with something that is in the map, that the thing that is not in the map is considered to be positive infinity, like arbitrarily large, and should be larger, right? So I'm going to help myself here by defining a separate data type which looks much like maybe, but I'm going to define it with a constructor that is called finite, c, and infinity. And I'm going to just derive EQ and ord for this, and I'm going to point out that the order of the constructors matters because the derived ord instance is actually taking the order of the constructors into account. And if I define infinity after finite, this will mean that if I do the same thing or the equivalent thing here, with
you mean infinity type, there, right?
Infinity, yeah, sorry. Thank you. And now infinity is actually greater than finite. So now I need a variant of the, let's derive show as well, just in case, a variant of the lookup function that returns these distance values. So let me just call that distance off. And this is going to take, I mean, it's going to look at this map, essentially. Right? It's going to do a lookup on this map. So let's just assume we have an info VC. And let's just assume we have a particular vertex, and we want to get the distance. Okay. And so here I get my info and I get my vertex, and I'm just going to do a lookup using the normal finite map lookup of the vertex into now the dist component of info. And I'm going to, this is the only language extension I'm using today, is the relatively recent overloaded record dot. So I'm going to use dot syntax to select the record field. So I want info.dist. And if this is nothing, then I'm going to interpret that as infinity. And if this is just of something, then I'm going to return finite of that thing. And yeah, here I also need to require ord of Okay, so this is a good amount of preparation, but now we are at a good point to actually tackle the actual algorithm, right? So we can actually try to write Dijkstra now, and let's keep in mind the structure that I already pointed out. So Dijkstra will get a graph VC, it will get a source, which is a V, it will get a nothing further, and in the end we want to return an info because we want to return this distant pref array. So that is the type. I'm going to do scoped type variables because we want to sometimes within the function give additional type signatures, which will again mention V and C, but they are not they're the same V and C that we're picking on the outside. So that means that we have to introduce a scope for them. That I still find it a little bit unfortunate that this is the syntax that has been established over the year for this in Haskell, but that's how it is. So we get our graph, we get our source. Let's try to keep the names mostly right, and let's consider what we already wrote here. So we want to kind of define a loop, which in itself should have the type we already established, that the loop should get the queue, which is a list of these, and an info, and produce a new info in the very end. So that's our loop. And then basically, yeah, this is just initialization. So in the end, like we're calling the loop with some initial values, and that is basically what this part here determines. And then the result of the loop is going to be the result of the entire function, because once the loop is done, then we are returning the info, and then the only thing that the function here does is returning these. So in order to figure out what we initially called a loop with, we just have to look at this part. And so the initial list of nodes is, if you look at this here, we are traversing all the vertices in the graph, and we're adding all the vertices to the list, to the queue, right? I mean, let's call this one queue here so that we have a name for it already, and this one info. So our initial queue is just all the vertices of the graph. So let's say graph dot and here we need an initial info. And so we need to say what the initial distances are and what the initial prev is. And so here, like if we look at it, like it almost looks like everything here is infinity and everything here is undefined. So we could just use empty maps for both, but we are then setting dist of source to 0. And that is the only like value that matters, that we actually have to insert into our finite map. So for dist, we can just use a singleton map that has a single binding from source to 0. And for pref, we can actually use an empty map. And yeah, and there are constraints missing here. So what do we actually need? Let's think about this. We need that the cost is numeric. We need that the cost can be compared. And we will need that the V type is in ord, because we want to use finite maps in order to store this. That is a price of our implementation. Okay, so now the only thing that is left is to like do the actual loop, right? And I mean, I already said that the structure is going to be something like this, where we want to like do some sort of case distinction, whether we have to like even continue. And the case distinction, whether we have to even continue, is sort of integrated in these first 3 lines, for which we already did some work, right? So this is basically the first thing we're going to do now is we're going to call our minViewOn function on a suitable first argument and on the queue. And then we have 2 results. Either we get back nothing, and that means we're done, right? I mean, this is like the queue is empty. And what does it mean when we're done? Like in a functional setting, we always still have to produce a result, but it just means that like whatever is our state, and that is sort of the queue and most prominently the info, we don't change, we don't do any further changes. So we return the info that we currently have unchanged once we're done. And in the other case, we get a minimum, which corresponds to this u, like the vertex with the minimum cost. And we get an updated queue. So this is the other like artifact of like turning imperative programs into functional programs, that like when we are within one loop iteration, we have to keep track of updates and actually explicitly declare new versions of data structures, right? So here we like perform a destructive update of Q, but in our functional language, we have to give it a new name, like the Q that does not have the element anymore, the U element anymore. So what do we need to put into this minViewOn? So that is our distance off. So we want like the what do we need here? Let's look again. We need a v to c function. That is exactly what we can get by calling distance off on our info.
Just to be clear, in distance in minViewOn, we said that we want a v to c for some c. We're instantiating that c here to distance c. Right?
That is true. That is true. Yeah. I should perhaps not have called it c. I was thinking about this, whether I should like give this completely different names like A and B or something like that. But now it's slightly misleading, but it's a good point, yeah, that you're pointing this out. Right. Okay. So that is this. Now the only thing that is left is this part. All right. So we have to like do another loop over all the neighbors. So we like over all the neighbors or v of u that are still in Q. That is what is being said here. So basically we want to take all the neighbors of u. Let's actually like just start with that. Just like do something like to consider. Let's call it to consider as a temporary name, like the things that we want to iterate here over. So we want to start with the neighbors of u. So that is like we are using graph.neighbors of u, and then we want to only consider those that are actually in the queue, like in the queue data structure, right? And Q at this point is actually, if we are precise, is Q prime, because we've already removed U from it. So we want to filter the ones that are elements of Q prime. Okay. And now we want to do something with every element of that list. And we can write another recursive function over that list. That is an option. But with a little bit more experience in Haskell, we can also recognize that this is a very common pattern, namely, like we have a state that we initialize, and that is again our info. That is essentially the values of the dist and the prev array. And then we're iterating over that list, and then every step we potentially update that state. And that is exactly the pattern that foldl prime covers, nicely connecting to our previous episode of the Haskell Unfolder. So we can actually just try to write this immediately as a foldl prime. But you don't have to, right? If you want, you can just write another recursive function. But let's just try to do this as a foldl prime, which operates on this list. And then we have to give it 2 more arguments. And this is now no longer consider. This is just this is actually just what we're doing.
Well, you need to call loop on this again, right?
Yes, you are right. I need to call Yes, this is going to give us a new state. Let's call it like this. Yeah, or new info.
Mm-hmm.
And then indeed, we need to call loop again. That is like the important point. In the end, on what is the new q? That is q prime. It does not change anymore after this removal. And on info prime.
Mm-hmm.
That's the thing that comes back from the foldl.
Yeah.
And here we need to feed it in the initial state, which is info. And we need to define an update function, right? Like this is like what to do for every node. And it has this type that is given here. Like it takes an info, like current state of distant prev, and a vertex. And it gives us a new info, which can be unchanged. In some cases, it will be unchanged, but it can be updated. So let's call this update. And let's just define update in here as well, which is of this type that it takes info VC and a V to an info VC.
Mm-hmm.
That's the final step that we still have to do. And this is fortunately actually relatively straightforward. I mean, there's not much more creativity involved, except for one thing. It is like we're slightly tricky with the types, right? There is this idea that we are looking at dist of u here, but dist of u can be infinite. And we're adding it to something else. And the way we define the cost function here, it is always finite, and that makes sense. And then here we are going to write the result of the sum potentially into the dist array. So we have to consider what happens here if this dist is infinite. Can it be infinite? This is actually an interesting question, right? And you have to think about the algorithm a little bit. But yeah, potentially it can be. That the way the algorithm is set up is that this is actually, you can be more clever about Dijkstra, but because we put everything into this Q data structure initially, all the nodes are in there. In particular, also nodes that are not even connected to the original graph, like these. And at some point, we'll have processed all the others, and we'll reach one of these unconnected ones. And then even the one with the minimum known distance can be infinite. But what it means in practice is that the moment we reach a node which has infinite distance, like in this minimum calculation, we have completely explored the connected part to the source node, and nothing changes anymore. In particular, once we are selecting, even if we're faithful to this, once we are selecting something that has infinite distance, this addition here will always be infinity as well, and it will not possibly be smaller than the previous dist value that has been here. So the moment we reach something that has infinite distance, we can actually stop. So that's why I'm proposing to actually make a change to the pseudocode at this point and deviate from this slightly. And already at this point, where we have determined the minimum, just add an additional check and just say case distance of info u off. And if this is infinity, then nothing can happen anymore. And we can just stop. We can stop the loop. And if this is finite with a distance of u, then we can do all this. But now this becomes a little bit easier, because now, in the update, what do we have to do? We have to compute alt, and alt is the du, which we now have, and is a normal number, and we can add it to the cost in the graph between u and v, and that is our alt.
We need arguments to update, right, on 73?
Yeah. Let's call it I and v, to not clash with the info that we already have in scope. And then we really, we check if alt is less than dist of v. So this is, again, we have to be slightly careful because distance of IV can be infinite, but alt is always finite, so we can simply compare the finite thing, right? And that will do the right thing. It will only evaluate to true in the cases we wanted to evaluate to true. And so if this comparison is wrong, like this is not even listed here, then again, we do nothing. So then we return our I unchanged, and otherwise we return a new info. And here we are having to basically update the array. That just means inserting into the finite map, because if we insert something into the finite map which is already in there, then it is overwritten. So here we're going to call map insert for v with alt in i.dist. And here we're going to call map.insert for v and u in i.dist. No, not an i.dist, an i.crash. Isn't it nice that the type checker catches all these things? And this is it. I mean, I'm not sure whether I did it all correctly, but I mean, hopefully this is it, right? And it is longer than the pseudocode version, because the pseudocode is glossing over a few things, right? Even though, like, usually you say functional code is shorter than imperative code. I think if you would transcribe this to a proper imperative language, it would be even longer, right? So this is still not bad, and it is relatively close, but it is also in some ways more explicit because the flow of the variables is more precise. So let's see whether we did this right. So I did actually, as a test case, define the example graph that I had been showing on the slides. So this should be the example graph which I had been presenting earlier here, this one. And we should be able to call Dijkstra on example with a start node of A, right? That is the one that we wanted. And so we get a make info, which is the final dist and the final prev. Slightly tricky to read. I mean, I can perhaps rearrange this here. And let's see. I mean, 11 is plausible, right? That is what we expected for F. That is at least plausible. And also, if we trace back the path, I mean, let me actually just go here, right? So 5 plus 4 is 9 plus 1 plus 1 is 10, 11. That is what we wanted. And from F, we should go back to D. From D, we should go back to E. From E to C, and from C to A. Let's see if that is also happening. From F, we are going to D. From D, we are going to E. From E to C, and from C to A. Yeah, I mean, of course, it's not a proper test, but it is plausible at least. Okay, yeah, I mean, we're quite a bit over time. Nevertheless, I want to say a few things, and perhaps there are also a few questions. I don't know. I want to say a few more things. Like, if you wanted to make it more efficient, right? There are a couple of obvious steps which have nothing to do with Haskell, which are just sort of like built-in inefficiencies even here. So, like, a typical approach to make Dijkstra slightly more clever is not to put all the vertices into this queue initially, but to actually maintain two containers of vertices, one being sort of the vertices that you definitely know you still have to look at, and one containing all the vertices that you already have completely processed. And the advantage, the already drastic advantage there, is that you can only add things, you will only add things to this definitely to look at list if they occur as neighbors of something. So you start by knowing that you only have to look at the source, but then every time you process something, you add the neighbors of that into this working set. And then the working set is much smaller. So already, like, just by doing that, like, the looking for the minimum distance will become much faster, because you're not looking at all the nodes all the time. You're also preventing that you're looking at sort of disconnected components at all, because you'll just never add them. right? So, and then the second step would be to pick a better data structure for this queue. That will also make a massive difference. And then you can like do some more subtle other tricks. But these are sort of the two most important things that are outstanding. And then one other remark I wanted to make before we conclude is that when I had just finished preparing this episode this morning, and I only saw this morning, I browsed the internet and found that on the Monday morning Haskell blog, like from August 22, not even that long ago, someone actually did something very similar, even with videos as well, and also took like the pseudocode for Dijkstra's algorithm from Wikipedia and translated into Haskell. And I only glanced at it briefly so far. I think many things are similar, some things are different, but I definitely want to point that out. It was not my intent to somehow, steal that person's idea. I mean, I think the only way it shows is that it is like sort of an obvious example to choose. But perhaps it is sort of interesting further reading because, I think a few more optimization and generalization tricks are being done there. Yeah, that's what I wanted to say. I'm not sure whether we have any questions. That would be nice.
There's one question. Would a set make sense for the queue? So I guess maybe you can say what should we? You mentioned that we could choose a different data structures. Maybe you could say a couple of words about what would be a good choice.
Yeah, so I think the ideal data structure you want is one that that makes this scanning for the minimum easy, right? And that is usually like heaps and priority queues are usually these data structures where you can like label something with a tag and you can extract quickly the minimum tag. Now, a set in Haskell is ordered, like is intrinsically ordered, and actually allows this extraction of a minimum. So it can be used to implement something like a priority queue, but it is not entirely trivial. I mean, it is doable, but it's not entirely trivial because you have to make sure that, like, because you're inserting the vertices into the set, right? But you're comparing against this distance order, and that is not the same thing. So you have to like tag something with its distance if you insert it into the set, and you also have to take into account that the distance can be updated. So then you have to like do some manipulation on that set. Like if you tagged it with its original distance when you inserted it, you have to make sure that you do something sane. So I mean, yeah, sure, you can use a Haskell set as essentially as a base structure for like on the fly implementing something like a priority queue or really building a priority queue on top. There are also libraries in Haskell that you can use that are ready made for that. But it is a good starting point indeed. So in that sense, it does make sense. One more remark, of course, is again, Dijkstra's algorithm is only an example. What you should actually be doing if you need Dijkstra's algorithm is not implement it yourself, or if you do it, only do it in order to learn about Dijkstra's algorithm or practice your Haskell. But you should use a ready-made library that like does that properly. And again, there are like quite a few good libraries that have like much more efficient implementations of Dijkstra's algorithm already ready-made, and also of related algorithms like A* or whatever you might need. Okay. That was the only question?
Yep.
All right. Then I guess we can...
Yeah, so thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And feel free to leave any comments below. We'll leave the chat open for a couple of more minutes if people want to ask any questions right now. And otherwise, you can always leave a comment and we'll answer it later. And we'll probably see you again in 2 weeks.
Yeah, thanks for your patience through this long episode. And I hope to see you back soon.